So now we come to week 8, the final week in our course. We'll start out, as usual, with the quotes of the week. And major topics this week, we'll build on some of the things we've been doing. First of all, traveling the galaxy. So this will come out of our analysis of the twin paradox last week. So we'll think a little bit more about that. Then talk about the famous equation, which of course is E equals mc squared, and how that fits into things here a little bit. Traveling the galaxy part 2, once we know a little bit about the famous equation energy, we'll say a few more words about what we were doing here in terms of traveling the galaxy and how feasible it is, how much fuel we might need to actually get someplace. Then we'll actually just spend a couple video lectures on the general theory of relativity, just to introduce a few of the key concepts here. We can't go into the details. This course isn't about that, plus it requires a lot more math than we want to tackle. But we'll start with the happiest thought, what Einstein termed the happiest thought of his life, or the most fortunate thought of his life. So we'll find out what that happens to be. And then another consequence of this happiest thought, actually, is the bending of light in a gravitational field. So we'll look at that. And then end up with making a few final comments on some topics we've touched on here and there, but want to emphasize a few points, such as the role of crucial experiments in science and in physics, such as the 1919 eclipse expedition that we'll talk more about. So the role of crucial experiments, the nature of genius, a few words on that, a few thoughts on that. Question of relativity versus relativism, what the difference between those is and how they are confused sometimes. And then end it off with a few comments on is this all really real? When we talk about time dilation, length contraction, some of these weird results, the twin paradox, is it really real? And so that's where we're going this week. And we'll also, of course, have a weekly summary at the end. And one final video summarizing some of the key concepts of the whole course. We won't try to recap everything, but just hit the high points, or our journey through the course, a roadmap, as it were. So the quotes of the week, though, for this week are actually particularly apt in terms of some of the things we'll be talking about. The first one is, if the facts don't fit the theory, change the facts. And this probably wasn't said by Einstein, but it certainly could have been said by him, as we'll see in some of our final comments when we talk about these crucial experiments. Another comment, he says, it strikes me as unfair and even in bad taste to select a few individuals for boundless admiration, attributing superhuman powers of mind and character to them. This has been my fate. And the contrast between the popular assessment of my powers and achievements and the reality is simply grotesque. And so, again, that will come into play, or keep that in mind when we talk about, under final comments, the nature of genius. Certainly, in some respects, we'd say Einstein was one of the supreme geniuses of all time in terms of scientific thought, but he had a somewhat different view of his powers and achievements, as it were. Then two other short ones here. When he was introduced to an 18-month-old baby, the baby screamed when introduced to him, and Einstein's response was, "You're the first person in years who has told me what you really think of me." Again, when you're lionized like Einstein was, sometimes it's hard to have people actually say what they think around you. And then finally, good advice for anyone is try to become not a person of success, but try rather to become a person of value. And with that more solid foundation, success in various ways will usually occur. So those are our quotes of the week. Here's where we're heading. And so in the next video, we'll talk about traveling the galaxy. Last week, we worked through the twin paradox, and if you've been thinking a little bit about it, you might be asking, can we put it to some practical use here? And so Alice has been thinking about that, so here's what she would like to do. She would actually like to take a trip to the center of the galaxy and back again. So she's going to be in the spaceship. Bob's going to be here on Earth observing her. Here's my fanciful drawing of the center of the galaxy. A lot of gas clouds around there. We actually can't see it in invisible light. We can study it using infrared telescopes and the like. And a lot of bright blue young stars there orbiting around actually a supermassive black hole with the equivalent mass of about 2 million solar masses, even more than 2 million solar masses. So very interesting region if we could actually get there. And Alice thinks she can do it. And so let's think about this using our analysis of the twin paradox. We know that in terms of Bob, the observer, it's a fairly straightforward analysis of the situation. Remember, Alice, the traveler, is a little more complicated there because we had some relativity of simultaneity, leading clock's lag going on and things like that. But from Bob's perspective, fairly straightforward. So let's think about it from his perspective here. He knows that it's actually about 30,000 light years to the galaxy. This is a round figure. It's not easy to actually figure out the exact distance. The best estimates right now are maybe around 27,000 light years or so. So we'll just round it up to 30,000 light years there. So we know the distance to the galaxy. So if you think about it, Bob is going to see, even if Alice moves pretty close to the speed of light here, if she could move at the speed of light, it would take her 30,000 years to get there, assuming we'll ignore the acceleration that's needed for the moment. Just assume she's going to constant velocity motion all the way there. 30,000 take 30,000 years traveling at the velocity of light from Bob's perspective. But remember, if he were to observe her clock that she's carrying with her, and that measures her time in her frame of reference, the Lorentz factor comes in, the time dilation factor. So we know that we'll just do half the trip because we know from Bob's perspective it's symmetrical. So coming back, it's the same thing. So we know from Bob's perspective that she travels not quite the speed of light, but very close to it. It's going to take about 30,000 years on his clocks. But we also know that as he observes her clocks, there's a time dilation factor. He observes her clocks ticking more slowly. And so it's going to be delta t, his perspective, divided by gamma. Well, let's say that Alice is really in a hurry here. She wants to get there in 2 years and then take 2 years back again. She could certainly, there's a slowing down factor as well. They have to account for that. But we're just doing a very rough calculation here. So we'll assume she can slow down pretty quickly and then get back up to speed pretty quickly and come back. Or even do something like, as she gets there, perhaps she can take a path through here, use sort of a slingshot effect around that black hole in the center, as long as she doesn't get too close to it, and shoot her back this way. So however she does it in terms of the details, we'll assume that we could work something like that out, or she could do it. So 30,000 years, for Bob, she wants to get there in 2 years. So if this is 2, we have, okay, Alice, she's in a hurry. She wants to get there in 2 years. Bob says, you know what, even if you go at the speed of light, it's going to take you 30,000 years. But her clock, he's going to observe her clock running more slowly. So if her clock is going to run 2 years on the trip from 0 all the way to 2 to get there, what does gamma have to be? Well, obviously very easily, 30,000, bring the 2 over here, 30,000 divided by 2. This implies that gamma equals 15,000. So that is the Lorentz factor that Alice needs to get to the center of the galaxy in 2 years, assuming constant velocity motion there. Well, what velocity is that? If you work that out using the Lorentz factor equation, here's what you're going to get. Assuming I got all the digits right here, it's something equal to this or very close to it. It's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 7, 7, 7, 7, 7, 8, or something like that. In other words, very, very close to the speed of light. And c here. We have the c at the end. So 0.99999 essentially times the speed of light to get a gamma factor of 15,000, which will enable Alice to get there according to her clock that she's carrying with her, and what she's aging according to, she'll get there in 2 years. and then maybe slingshot back in another 2 years back this way. So she's back in 4 years. And she gets back, and she's really excited to tell Bob, gosh, that was fantastic, all the great stuff, took some great photographs there, comes back, and when she asks, okay, where's Bob? It's like, well, Bob who? If you think about it, you know, Alice has aged 4 years total. People on Earth, though, time on Earth, 30,000 years there, 30,000 years back, and it's 60,000 years later on Earth when she gets back. And in fact, so you can think of this somewhat as time travel into the future would actually be possible here with the twin paradox analysis or anything similar to that. So it's not only, you know, at that point, it's Bob Jr., Bob the Third, Bob the Fourth. It's more like Bob the 600th. You know, might still be around at that point. So about 600 generations have passed. So it'd be very interesting for Alice not only to experience the center of the galaxy, what's going on there, but to come back and see what Earth is like 60,000 years later, if anyone is even still around at that point. Another interesting question here is a couple interesting questions. One is, what would Alice actually see if she could take this trip as she speeds along toward the center of the galaxy? And of course, in films like Star Wars and Star Trek, you get the idea of you see the stars sort of flowing by you, streaks of light. And in fact, the image we use for this course, if you look on Coursera, it has sort of that effect, right? Sort of the stars streaming by on a blue background. In actual fact, if you do the analysis, it wouldn't be quite so dramatic, unfortunately. It would be more just like a fuzzy glow that you would see. In fact, not only that, it'd be a very dangerous type of situation for her, because here's what would happen. Remember how we talked earlier in the course about the Doppler effect and train whistles? We've got a train whistle coming towards us, or if we're moving toward it, you get the higher pitch, and then as it moves away, it's a lower pitch. In other words, the frequency of the train whistle increases as you move toward it. Same thing here with light. There's a Doppler effect, and even a relativistic Doppler effect. But as Alice moves at that velocity and sees stars coming to her, the light from those stars would be shifted toward the blue end of the spectrum. And even beyond that, into the ultraviolet region, and beyond that, into what's known as the extreme ultraviolet region, and beyond that to the X-ray region. In other words, all those stars that she's approaching, the light from those stars coming at her would be X-rays. And so she'd need some pretty good shielding on her spaceship to protect her from those X-rays during her trip. Now, of course, we can't see X-rays. So in other words, the idea here is the visible light from those stars, because of the extreme Doppler shift, the frequency shift there, would turn the visible light into X-rays coming at her. And some of you may know that throughout the universe, there's what's called the cosmic microwave background radiation. It's sort of a remnant of the Big Bang, and it's, as the name implies, microwave radiation. And what would happen is, and that sort of pervades all of space. We see it coming from all different directions in space. There's some slight differences in certain directions, but for the most part, it's uniform throughout the universe, as best we can tell. Well, that's in the microwave region. What would happen is that radiation, which is electromagnetic radiation, would be shifted into the visible region. And so this fuzzy glow would be all around Alice as she traveled to the center of the galaxy and back at a very high velocity. So she would actually see the cosmic background radiation, cosmic microwave background radiation, as a fuzzy glow all around her in the visible region of the spectrum. So that's what she would see. Not quite as dramatic as the stars flying by as she travels. Let's also, though, ask the question, how realistic is this? Because one thing is, how fast does she have to accelerate to get up to a speed like this? So let's just consider that for a minute. We'll leave the V number here, and we'll remind ourselves that gamma is 15,000 to get us there. So let's think about this. We know that us humans, we can't stand more than certain types of acceleration. And so we want a relatively gentle acceleration for the spaceship, but enough to get Alice up to speed fairly quickly. So let's just say, what if the acceleration equals 10 meters per second squared? In other words, What that is saying is 10 meters per second per second. So her velocity increases by 10 meters per second every second. That's literally what acceleration is. 10 meters per second squared is 10 meters per second every second. So it's increasing again 10 meters per second every second. That's roughly the acceleration due to gravity, which is 9.8 meters per second squared. And we know we can live in that type of environment. So a first spaceship had a constant acceleration of 10 meters per second squared. She would feel pushing on her just the normal force of Earth's gravity. And so presumably that would work. So if we could have that constant acceleration, how long would it take to get up to essentially the speed of light or very, very close to it? Just do a simple calculation. Well, the formula is velocity is acceleration times time, just a times the elapsed time that you're going with it. And so we know the velocity here is essentially c, 0.9999 times c. Acceleration is 10. So essentially the velocity is, let's just say, we'll get right up to the speed of light. So we know that's 3 times 10 to the 8th meters per second. In other words, really 0.999999 times that, but we'll just round it to 3 times 10 to the 8th meters per second, equals, acceleration here is 10, that's what we're assuming, times the time. How long is it going to take us to get up to this using acceleration of 10 meters per second squared? Well, you do the math there. It's not too difficult. Convert it into days, say, and you find that t is approximately equal to 347 days. And you think, wow, hey, that's not too bad. If I can accelerate at a reasonable acceleration like that for 347 days, I'm up to essentially the speed of light. And so Alice's trip then looks maybe a little more promising. Unfortunately, there's another catch here. And that catch is the energy involved to do something like this. Because a little later on this week, we'll talk about the famous equation, E equals mc squared. That also came out in the miracle year of 1905 in Einstein's September paper. So we'll get to that. But just to let you know, one of the results that come out of that is the energy involved to accelerate as you get up to speeds close to the speed of light also increases by gamma. And therefore, what happens is, remember, as v gets very close to the speed of light, gamma gets larger, 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 and tends toward infinity. So really, to get up to these speeds close to the speed of light takes massive amounts of energy for any relatively large mass like a spaceship. We can actually get subatomic particles going that fast, but even a subatomic particle takes a lot of energy to do that. So unfortunately, not very practical there, unless we could come up with some way to generate a lot of energy and design a spaceship to do it, and so on and so forth. One more thing, though, you might say, well, maybe we don't need to get all the way up to here. What if we just said, what if we could just take the trip at 9/10 the speed of light? Okay, so maybe that would reduce the energy requirements, perhaps, and maybe it's more practical that way. But remember what happens then to gamma. With v equals 0.9c, gamma is about 2.3 for that. And with gamma equals 2.3, so well, maybe the energy, if energy requirements sort of scale according to gamma, perhaps that isn't so bad. But remember what that does to Alice's trip now. Remember the time on her clock is 30,000 years divided by gamma, as Bob sees it, as he's observing her clock, and as she's observing her clock tick as well. And therefore, if gamma is only 2.3, then the time on Alice's clock that ticks off on her journey to the center of the galaxy is about 13,000 years. And so clearly she's not going to make it even close, nowhere near the center of the galaxy. She won't even get to the next star, really, before she gets old, unfortunately. So traveling the galaxy, yes, it is certainly possible in theory. And we can imagine situations like that. But the amount of energy involved is just way beyond our capabilities at the moment. And yet, we do see effects like this, certainly with, as we've talked about before, in the twin paradox in the subatomic world, where we can actually get particles up to that speed, whether they're artificially accelerated or naturally accelerated like the muon example we did. So unfortunately, have to burst our bubble in terms of traveling the galaxy. We don't have anything like warp drives that we know of at the moment, but who knows? Perhaps someday in the far distant future, we'll figure something like that out.